We interact with mirrors all the time, right? Brushing our teeth, checking the rear view, but the science of light and reflection? Oh, it goes way beyond just a flat pane of glass. Today on The Explainer, we are diving straight into the mind-bending geometry of how curved mirrors literally shape our reality. Think back to a time you walked into a funhouse. Let's imagine a girl, Mina, doing just that at a science center. She's standing in front of this row of wacky, curved mirrors. Up close to one, her face looks absolutely massive. But she glances over at her brother further down the hall, and in his mirror, he's completely upside down. And then in yet another one, she looks like a tiny miniature version of herself. It's confusing, right? It totally threw Mina for a loop.
And that brings us to the core mystery of our explainer today. Why do curved mirrors distort our reflections so dramatically? How is it that a simple curve on a piece of shiny glass can completely rewrite the basic rules of what we see, turning the world upside down or shrinking it to a miniature scale?
Well, we've got a roadmap for figuring this out. First, we'll recap the funhouse mirror mystery. Then we'll meet the spherical mirrors. After that, we'll explore changing shapes and sizes, check out curved mirrors around us, and wrap up with the absolute laws of reflection.
All right, moving right along to section 2, meet the spherical mirrors.
So by definition, a spherical mirror is a mirror whose reflecting surface is shaped like a part of an imaginary hollow glass sphere. Now here's the catch. They aren't actually manufactured by taking a giant glass bubble and slicing it up like an orange. Actually, what happens is a flat piece of glass is perfectly ground and polished into a very specific curve. Then, they add a highly reflective coating, like a super thin layer of aluminum, to make it act like a mirror. And depending on exactly where they put that reflective coating, we end up with two completely distinct types of mirrors. You've got the concave mirror, where the reflecting surface curves inward. Think of it like a cave you can walk into. On the flip side, we have the convex mirror, where the surface curves outward, bulging right towards you. Now, you actually have a flawless example of both of these sitting in your kitchen right now. I'm talking about a shiny metal spoon. Seriously, a simple spoon acts as both types of mirrors. The inner curve, that's your concave mirror, and it's going to show you an inverted, upside-down image of yourself. But flip it over to the outer convex curve, and suddenly your face is erect, meaning upright, but noticeably smaller. I honestly highly encourage you to test this out. Go grab a shiny spoon, hold the inner hollow curve close to your face, and then slowly pull it away. Watch how your reflection shifts. Then flip it over to the bulging side and do the exact same thing. It is such a brilliant, hands-on way to watch the physics happen right in front of you. Okay, let's jump into section 3, changing shapes and sizes. So unlike your standard flat plane mirror in your bathroom, which always gives you a perfect one-to-one reflection, spherical mirrors actually change the size of the image based on how far away you are from them. Take a toy dog placed in front of one, for example. As the distance between the dog and the mirror changes, the size of its reflection completely transforms.
The big takeaway here is this. If you start close to a concave mirror and slowly step back, your reflection is eventually going to flip upside down. It inverts. But if you're looking into a bulging convex mirror, your reflection is always going to stay erect and upright, literally no matter how far back you walk. Let's see how this plays out in the real world. Section 4, curved mirrors around us.
Concave mirrors, those are the inward curving ones, are absolutely crucial when you need to enlarge a close-up view or heavily focused light. That is exactly why your dentist uses one. When they stick that tiny mirror in your mouth, the concave shape gives them a magnified, supersized view of your teeth. You'll also find these acting as reflectors inside flashlights and car headlights to focus the beam, and they're even used as the primary mirrors in massive reflecting telescopes to help astronomers study deep space. On the other hand, we have everyday convex mirrors. Remember, these are the ones that always form an upright but much smaller image. Because they shrink the image down, you can cram way more of the background into the reflection. This gives drivers a dramatically wider field of view of the traffic behind them. It's the exact reason they're used as side view mirrors on cars, as safety mirrors at blind intersections, and even as surveillance mirrors up in the corners of stores. Which brings us to our final stop, Section 5, the laws of reflection. To really master this, we just need to map out the basic geometry of light. First up is the incident ray, which is simply the light traveling toward and falling onto the mirror. Next is the reflected ray, which is the light bouncing right back off. And to measure the angles, we use something called the normal, which is just an imaginary line drawn at a perfect 90-degree angle right at the exact spot where the light hits the surface. And that brings us to law number 1, the angle of incidence, which is the angle between the incoming ray and that 90-degree normal line is always exactly equal to the angle of reflection, period. Whether light hits a perfectly flat bathroom mirror or the crazy curved surface of a funhouse mirror, it bounces off at the exact same angle it came in. It's just a fundamental rule of the universe. Then we have law number 2, which states that the incident ray, the normal, and the reflected ray all lie in the very same plane. Think about it like this. If you shine a flashlight onto a flat sheet of paper sitting on a table, the reflected beam runs right along the surface of that paper. But if you bend the edge of the paper off the table, the reflected beam instantly disappears from the bent part. That bending creates a brand new plane. The light absolutely requires the incoming ray, the bouncing ray, and the normal to align perfectly on one single flat plane.
So taking everything we've talked about, think about those convex side view mirrors on your car. Why do they always have that safety warning printed on them? Objects in mirror are closer than they appear. Well, based on what we just learned about how convex mirrors inherently shrink images to show a wider view, why might a driver be completely fooled about the actual distance of the car creeping up behind them? Think about that the next time you check your blind spot. Thanks for joining the explainer.